IMs are capable of self-refresh. No external logic is required to instruct the Dram to refresh or provide a RAW address. Under some conditions, most of the data in Dram can be recovered even if the Dram has not been refreshed for several minutes. 29. Memory timing. Many parameters are required to fully describe the timing of Dram operation. Here are some examples for two timing grades of asynchronous Dram, from a data sheet published in 1998. Sad Smiley 30. 50 ns 60 ns description tar C84 ns 104 ns random read or write cycle time, from one full /RAS cycle to another. TIC 50 ns 60 ns access time /RAS low to valid data out RCD 11 ns 14 ns /RAS low to /CAS low time AIS 50 ns 60 ns /RAS pulse width, minimum /RAS low time. TRP 30 ns 40 ns /RAS precharge time, minimum /RAS high time. TPC 20 ns 25 ns page mode read or write cycle time, /CAS to /CAS. TAA 25 ns 30 ns access time, column address valid to valid data out, includes address setup time before /CAS low. TCAC 13 ns 15 ns access time /CAS low to valid data out. CAS 8 ns 10 ns /CAS low pulse width minimum. Thus, the generally quoted number is the minimum /RAS low time. This is the time to open a RAW, allowing the sense amplifiers to settle. Note that the data access for a bit in the RAW is shorter, since that happens as soon as the sense amplifier has settled, but the Dram requires additional time to propagate the amplified data back to recharge the cells. The time to read additional bits from an open page is much less, defined by the /CAS to /CAS cycle time. The quoted number is the clearest way to compare between the performance of different Dram memories, as it sets the slower limit regardless of the row length or page size. Bigger arrays forcibly result in larger bit line capacitance and longer propagation delays, which cause this time to increase as the sense amplifier settling time is dependent on both the capacitance as well as the propagation latency. This is countered in modern Dram chips by instead integrating many more complete Dram arrays within a single chip, to accommodate more capacity without becoming too slow. When such a RAM is accessed by clocked logic, the times are generally rounded up to the nearest clock cycle. For example, when accessed by a 100 MHz state machine, i.e. a 10 ns clock, the 50 ns Dram can perform the first read in 5 clock cycles, and additional reads within the same page every 2 clock cycles. This was generally described as 5222 timing, as bursts of 4 reads within a page were common. When describing synchronous memory, timing is described by clock cycle counts separated by hyphens. These numbers represent TCL, TRCD, TRP, TIS in multiples of the Dram clock cycle time. Note that this is half of the data transfer rate when double data rate signaling is used. JEDEC standard PC 3200 timing is 3448/31, with a 200 MHz clock, while premium-priced high-performance PC 3200 DDR Dram DIMM might be operated at 2225 timing. 32. PC 3200, DDR 400, PC 2-6400, DDR 2-800, PC 3-12800, DDR 3-1600. Description: typical fast, typical fast, typical fast, cyclist time, cyclist time, cyclist time, cyclist time, cyclist time, cyclist Emetical 315 ns 210 ns 512.5 ns 410 ns 911.25 ns 810 ns /CAS low to valid date out, equivalent OTCAC. TRCD 420 NS210 NS512.5 NS410 NS911.25 NS810 NS/RAS low to /CAS low to mitar P420 NS210 NS512.5 NS410 NS911.25 NS810 NS/ICE pre-charge time, minimum pre-charge active time. TIS 840 NS525 NS1640 NS1230 NS2733.75 NS2430 NS-RO active time, minimum active tar pre-charge time. Minimum random access time has improved from TIC equals 50 ns to TRCD plus TCL equals 22.5 ns, and even the premium 20 ns variety is only 2.5 times better compared to the typical case, 2.22 times better. CAS latency has improved even less, from CAC equals 13 ns to 10 ns. However, the DDR3 memory does achieve 32 times higher bandwidth. Due to internal pipelining and wide data paths, it can output 2 words every 1.25 ns, 1600 word/s, while the EDO Dram can output 1 word per PC equals 20 ns, 15 word/s. Timing abbreviations. TCL CAS latency. TCR command rate. TP pre-charge to pre-charge delay. TRAS RAS active time. TRCD RAS to CAS delay. TREF refresh period. TRF0 refresh cycle time. TRP RAS pre-charge. TRRD RAS to RAS delay. TRTP read to pre-charge delay. TRTR read to read delay. TRTW read to write delay. TWR write recovery time. TWTP write to pre-charge delay. TWTR write to read delay. TWTW write to write delay. Memory cell design. Each bit of data in a DRAM is stored as a positive or negative electrical charge in a capacitive structure. The structure providing the capacitance, as well as the transistors that control access to it, is collectively referred to as a DRAM cell. Few are the fundamental building block in DRAM arrays. Multiple DRAM memory cell variants exist, but the most commonly used variant in modern DRAMs is the 1 transistor, 1 capacitor, 1T1C cell. The transistor is used to admit current into the capacitor during writes, and to discharge the capacitor during reads. The access transistor is designed to maximize drive strength and minimize transistor leakage, Kenner, PG34. The capacitor has 2 terminals, one of which is connected to its access transistor, and the other to either ground or VCC/2. In modern DRAMs, the latter case is more common, since it allows faster operation. In modern DRAMs, a voltage of plus VCC/2 across the capacitor is required to store a logic 1, and a voltage of VCC/2 across the capacitor is required to store a logic 0. The electrical charge stored in the capacitor is measured in coulombs. For logic 1, the charge is, where Q is the charge in coulombs and C is the capacitance in farads. A logic 0 has a charge of 33. Reading or writing a logic 1 requires the word lin is driven to a voltage greater than the sum of VCC and the access transistor's threshold voltage, VTH. This voltage is called VCC pumped, VCCP. The time required to discharge a capacitor thus depends on what logic value is stored in the capacitor. A capacitor containing logic 1 begins to discharge when the voltage at the access transistor's gate terminal is above VCCP. If the capacitor contains a logic 0, it begins to discharge when the gate terminal voltage is above VTH. 34. Capacitor design. Up until the mid-1980s, the capacitors in drum cells were coplanar with the access transistor. They were constructed on the surface of the substrate, thus they were referred to as planar capacitors. The drive to increase both density and, to a lesser extent, performance, required denser designs. This was strongly motivated by economics, a major consideration for DRAM devices, especially commodity DRAMs. The minimization of drum cell area can produce a denser device and lower the cost per bit of storage. Starting in the mid-1980s, the capacitor was moved above or below the silicon substrate in order to meet these objectives. Dram cells featuring capacitors above the substrate are referred to as stacked or folded plate capacitors. Those with capacitors buried beneath the substrate surface are referred to as trench capacitors. In the 2000s, manufacturers were sharply divided by the type of capacitor used in their DRAMs, and the relative cost and long-term scalability of both designs have been the subject of extensive debate. The majority of DRAMs, from major manufacturers such as Hynix, Micron Technology, Samsung Electronics, use the stacked capacitor structure, whereas smaller manufacturers such Mania Technology use the trench capacitor structure. Jacob, pp. 355-357. The capacitor in the stacked capacitor scheme is constructed above the surface of the substrate. The capacitor is constructed from an oxide-nitride oxide, ONO, dielectric sandwiched in between two layers of polysilicon plates. The top plate is shared by all drum cells in an IC, and its shape can be a rectangle, a cylinder, or some other more complex shape. There are two basic variations of the stacked capacitor, based on its location relative to the byte line: capacitor over byte line, COB, and capacitor under byte line, CUB. In a former variation, the capacitor is underneath the byte line, which is usually made of metal, and the byte line has a polysilicon contact that extends downwards to connect it to the access transistor source terminal. In the latter variation, the capacitor is constructed above the byte line, which is almost always made of polysilicon, but is otherwise identical to the COB variation. The advantage the COB variant possesses is the ease of fabricating the contact between the byte line and the access transistor source, as it is physically close to the substrate surface. However, this requires the active area to be laid out at a 45-degree angle when viewed from above, which makes it difficult to ensure that the capacitor contact does not touch the byte line. CUB cells avoid this, but suffer from difficulties in inserting contacts in between byte lines, since the size of features this close to the surface are at or near the minimum feature size of the process technology. Kenner pp. 3342. The trench capacitor is constructed by etching a deep hole into the silicon substrate. The substrate volume surrounding the hole is then heavily doped to produce a buried N-and plate and to reduce resistance. A layer of oxide-nitride oxide dielectric is grown or deposited, and finally the hole is filled by depositing doped polysilicon, which forms the top plate of the capacitor. The top of the capacitor is connected to the access transistor's drain terminal via a polysilicon strap. Kenner, pp. 42-44. At trench capacitors, depth to width ratio in DRAMs of the mid-2000s can exceed 51. Jacob, p. 357. Trench capacitors have numerous advantages. Since the capacitor is buried in the bulk of the substrate instead of lying on its surface, the area it occupies can be minimized to what is required to connect it to the access transistor's drain terminal without decreasing the capacitor's size, and thus capacitance. Jacob, pp. 356-357. Alternatively, The capacitance can be increased by etching a deeper hole without any increase to surface area. Kenner, pg 44. Another advantage of the trench capacitor is that its structure is under the layers of metal interconnect, allowing them to be more easily made planar, which enables it to be integrated in a logic-optimized process technology, which have many levels of interconnect above P substrate. The fact that the capacitor is under the logic means that it is constructed before the transistors are. This allows high-temperature processes to fabricate the capacitors, which would otherwise be degrading the logic transistors and their performance. This makes trench capacitors suitable for constructing embedded Dram, EDIM, Jacob, P357. Disadvantages of trench capacitors are difficulties in reliably constructing the capacitor structures within deep holes and in connecting the capacitor to the access transistor's drain terminal. Kenner, pg 44. Historical cell designs. First generation.
Yes. Need take a break because I'm to wash my clothes in the bathtub. I'm out of underwear, so I need to start again, wash my clothes in the bathtub. I don't know where all my underwear is, but it's gone. So I had a few pair of new underwears, but I still save, so I just wash this, but I don't have like 30 pairs of underwears like 1 year ago. I don't know where it is. So I have to do this, but I do this in Danish. So I will charge the camcorder. I will start upload this a little bit. I have to do this dishwashing. Then I could start upload this.